Okay, but I'm not going to do 6 points. Okay, we're going to do this using the technique of step index logical relations. All right? So far, and until 2000, I think, yes. Until 2000, so 12 years ago, logical relations were always defined by induction on the structure of types. And then extending them to settings where you had even recursive functions and recursive types and let alone mutable references. All of these more advanced features where you have certain kinds of circularities creep in and types start to get bigger. It was really hard to extend logical relations to those settings. And people did come up with logical relations that did that, but they were essentially denotational in flavor, and they used rather complicated math, functors, et cetera, in order to do it. Okay? Step index logical relations are sort of, okay, first of all, step index logical relations fall into this category of the operational kind of logical relations. So I just mentioned denotational logical relations, where you essentially interpret types using some sort of mathematical objects. You say V of tau is inhabited by some sort of mathematical functions, etc. Okay? We're not doing denotational version of logical relations. We're not doing denotational semantics. We're using a very operational flavor of logical relations. That's why you see, when does an expression E belong to E of tau? Oh, let's go run it. Okay? That's going to happen over and over again. We sort of run things to see if they behave like the thing that we expect. Okay? All right. So now, step index logical relations. Basically, here the problem is that the types are getting larger. With step indexing, we're going to extend our logical relation slightly. We are going to say, we're not just going to say that some value V belongs to the value interpretation of tau. We're going to say that value V, I'm going to put a natural number here, 0 or greater. This is our step index. And here's how you want to read this. Some value V looks like it has type tau for up to k steps. So if I give you a V that belongs to tau for k steps, you can go do anything with that value that you like, but you only have k steps within which nothing will go wrong. If you run more than k steps, if you try to do something with this value beyond k steps, then it may actually get stuck or not behave like what you expect. Okay? So I'm sort of approximating what I know. Yes?
What was nice about the system before the step index is that we can distinguish between error, like a real stuck state and a looping state. Right? But once you introduce the step index, then
well, I mean, it'll still work out. I mean, what do you mean by we can distinguish between a real stuck state and a looping state?
So let's say
that basically says that if you're looping, then I have nothing to show. Right? The definition of E tau says if I give you an expression and it just keeps looping, so then in order to show that that expression behaves like it has type tau, you don't really need to prove anything, right? Because if you look at the definition of E tau, it says for all E primes, so when you run E, you get to an irreducible state. Since your expression loops,
you only need to prove anything when it's looping. But now, the case where the k is...
Let's see how it works out. Okay? You what?
You would use large case.
Large K? Oh, you want me to write a big K? Sorry.
I mean, if you compute this interpretation with k equals 10,000,
yes. And actually, that's the whole point. Eventually, what you want to do is, in your definitions, we want to define things at some up to some approximation, but in the end, you want to do your proofs for all k. Okay, so let's see that. So, read this as value V behaves like it has type tau for k steps. Let's go edit our definitions. When does a value behave like a Boolean for k steps? Or what are the values that behave like Booleans for k steps? It's true and false, right? We don't need to do anything else. Right? Okay. Now let's put a k here. I'm giving you, right? Ah, okay. That's what Benjamin is pointing out. And I was trying to avoid that for 2 more minutes. I will come back to that in a second. Okay. So basically what I've just done is I haven't put any arbitrary values here, right? I've put values that type check, right? I said this in the beginning that I'm always going to build these value interpretations out of values that syntactically have the right type. Okay? So that's why I only have true and false here. What Benjamin was asking is, why can't I put an arbitrary value, say that an arbitrary value is in there for 0 steps? I'm just not going to do that. I'll take care of that in a different way. So just hold that thought for a second. All right. So let's talk about when functions behave like they have type tau 1 arrow tau 2 for k steps. Okay. So you have a lambda term. I give you a lambda term. All right. What can you do with it? You have k steps to run. What can you do with it? To test if it's not a lambda. That's what you're doing here. Think of yourself as the adversary. I'm going to give you something and say you have k steps, and you're going to try to, do things with it to figure out, to make it, behave in certain ways and test if that assumption goes wrong. Okay? All right. So, have a lambda term. You have k steps. What can you do with it? Apply it. Okay, but you could either apply it now or at some point in the future, right? So in particular, you might be in the middle of a big program expression where you have a lambda being applied to some argument, and maybe your program needs to take some, you need to take some steps to evaluate the argument down to a value. All right, so you can, if I give you a lambda, you can apply it either now or in the future. Okay, I'm going to capture that by saying lambda x dot e behaves like it has type tau 1 arrow tau 2 for k steps if at some point in the future, when we have j possibly less than k steps left, if at that point you give me an argument that is good for the remaining number of steps, which is j, then after beta reduction, e with b for x should be good for j steps as well. Okay? All right. Now, when does an expression behave like it has some type tau for up to j steps? All right, so I'm going to put a k here. So an expression E behaves like it has type tau for k steps if what? Well, so k is the max you have. All right, so we're going to say, basically you're going to take E and you're going to run it for a while till it gets to a value. Right? So for some, suppose that for some j strictly less than k, suppose that E reduces to E prime in j steps. Okay, so I started out, I'm trying to figure out if this expression behaves like this type for k steps. I started out with k. I used up j of those steps to get to this irreducible point. Now how many steps do I have left? K minus j. So my E prime should behave like a value of type tau for k minus j. Okay? All right. Now, coming back to the point of what happens when you have 0 steps left. When I have 0 steps left, is this true? Sorry. Does true behave like a function of type bool arrow bool for 0 steps? Yes, it does. Okay, so in particular, then something like lambda x bool dot true looks like it has type bool arrow bool for 1 step, right? Because if I give you a lambda, this guy looks like it's a function for 0 steps. Okay, now let's make that the body of this lambda. Now you have a lambda. What can you do with it? You can apply it to something, right? In fact, I could, let me put a v here. I don't even need to put a v here. This lambda belongs to the value interpretation of this function type for 1 step. Why is that? Because you only have 1 step, So you can apply this to some Boolean value, and then you need to show that the body has behaves like an expression of type bool arrow bool for the remaining number of steps, which at that point will be 0. Okay? Oh, okay. Ask more. Okay.
With the current definition of K of T1 to T2, it looks like we may substitute in the body and then test for Ej, which may be equal to K.
Okay, good point. All right, so okay, we're defining this logical relation now by induction, by primary induction on these number of steps, and secondary induction on the types. Okay, so that's what we're doing. Keeping that in mind, let's look at what's going on at the well-foundedness of this bit of the definition. So we're trying to define the interpretation of tau 1 arrow tau 2 at k steps. And in the definition, we are using k, j, which could be k, because I put a less than or equal to here, right? So my point is that the step index might not get smaller, but the type gets smaller, so we're still okay. Alternatively, you could perfectly well write this definition with a j strictly less than k over there. Because if it's a lambda, you will always take one step before you need to, show anything. So that will work out fine as well. Okay, so here's one idea. I should draw this timeline. We're over here. We have k steps left. And we have a lambda. I'll just write lambda x dot e. At some point in the future, when we have j steps left, let's say when we have j plus 1 steps left, someone gives us a value. And now we're going to take our lambda x dot e and apply it to that value. This beta reduction step is going to eat up exactly one step. And now you will have j steps left. Okay? So at this point, this expression will have stepped to e with v for x. That's what we have when we have j steps left. So now we just need to show that the e with v for x is good for the remaining j steps. With j equals 1? Yeah.
So if it's j less than or equal to k, then you can't prove that.
Oh, you're absolutely right. I was using j. Okay, yes, you're right. So let's use j strictly less than. But even if it doesn't work for the example, the logical relation is perfectly good even then. If you put a less than or equal to there. There's no problem with well-founded. Okay.
I have a question.
Yes.
So the timeline, or help me realize what I'm tripping on with the V case for lambdas. What's the equation for the J index on the V for tau 1?
So you expect this to be j plus 1?
I feel like it should be the difference between K and J plus 1. Like, at J plus 1, we got this V, and it seems like it should have taken some amount of steps with that to accommodate.
But you see, between here and here, someone else already took the steps. Okay? Someone else already took steps to get our argument down to a value. And this definition says, give me an argument that is already a value. Does that help?
That will behave like a value for J steps?
J is the number of steps you have left.
J is the number of steps that you have left.
I'm going to spin those evaluating the result of the substitution. So what does this have to do with?
Which may involve evaluating.
Which may involve evaluating the things plus.
So at max, it would be, at maximum, all those would be spent on J, or on the evaluating V.
On evaluating this value?
Right.
Well, this is already a value, right?
Yeah,
so don't worry about what happens.
Why does it need any steps at all?
Sorry?
So why does it need any steps at all?
Why does it need any steps at all? Good point. This comes back to why are we building a logical relation at all, in the sense that we, okay, what you're sort of saying is that this is already a value. What does the intuition about the remaining number of steps help with? Right? It's already a value.
estimate itself as a function, though.
Yes, this is analogous to what we were talking about yesterday with strong normalization. Why do we need to show that lambda, like why do we need to worry about lambda belonging to the set well, because at some point you can apply that lambda, and then the body sitting inside the lambda is the thing that you will be able to run. That's the intuition. That's what this remaining J steps is for. So this function could be taking as its argument another function. Right. And you could, this could be another function. And then inside here, you could apply that function. So you need to have some sort of, you need to control how many steps you have allotted for that to run. Does that help? Yeah.
Clear that we need one of those inclusions to be strict. Do we have a free choice of which one it is?
As in this one, or either the types can get smaller, or the step index.
No, one of the step indexes has to be a strict less than.
Yes, absolutely. So I always insist that this be strictly less than.
Would it break if we did it the other way around?
I'm not sure. I would have to test it out. Yes.
How come true is the number of zero?
Oh, okay. So I claim that true belongs to, let's look at the definition. Let's see if we can show that true belongs to E0 bool-Arab-bool. In order to show that true belongs to bool-Arab-bool for 0 steps,
Find something smaller like what?
there's nothing smaller than 0. That's precisely my point, right? So basically, you have to go and immediately pick a number smaller than 0. If given a number smaller than 0, you can show that, this reduces to, basically, since there is no number smaller than 0, it's factorlessly true.
Okay. So you can put whatever.
Yes, you can put whatever there. So every term looks like it has any type whatsoever at 0 steps. And every term belongs to the relation at 0 steps. Yes.
I'm confused about the exchange that Judy just had. So, what would go wrong if we let both of? I mean, is it a foundational issue that comes up if both of those are non-strict equalities?
Oh, if both of these are non-strict equalities?
Yeah.
Let's look at it. Okay, so this is a very, very good one. I should point this out. All right, so if this is a non-strict equality, right, then we have a k here. J can be equal to k. So we're examining whether or not this definition is still well-founded if this is less than or equal to this. Okay, so J can be equal to k. That means we have a k here, and in particular we have a k here. All right. Now we go here, and this is which looks fine, except when we add recursive types, we're not going to be fine. So let's add recursive types. Let's edit the definition of recursive types. Yes.
Just one question. I'm not so sure, well, this is a problem, but it seems to me like we are trying to define recursive types, but the definition we're using the natural numbers. So, I mean, the natural numbers will be defined as a recursive type. So
Right, but this is sort of a meta theory, right? This is a building model. So
we're assuming we already
we're
know
assuming
the
we
natural
have
numbers, and then we
numbers.
will build them as a recursive type.
And I can't prove we're not trying to
we're not trying to encode the natural numbers themselves, these J's and K's, we're not trying to encode them themselves.
Yes, you're assuming that they
You're
exist, they are
assuming that
well
they
ordered, and
Exactly, absolutely. Everything that you assume about natural numbers, absolutely.
We're also assuming that sets exist.
okay, but not like a recursive type.
Okay, so I'm going to put a K here. This is why we added step indexing at all, right? Because this definition was not well founded. All right, so now let's try to figure out. Fold V belongs to this type for K steps if what? Right, we want to reduce the step here. So I'll just say for all J strictly less than K, V belongs to the bigger type for j steps. You could even put k minus 1. Yes, absolutely. So you could put j strictly less than k, or you could just put k minus 1. If you put k minus 1, you have to be a little bit careful in a proof later on. That's all. That's precisely where. Yeah. Okay, so sorry, what's your name? Gabriel. Okay, so what Gabriel just mentioned is that we want a form of monotonicity, right? I keep saying that V looks like it has type tau for up to k steps. So if I give you a value that looks like it has type tau for 5 steps, should it look like it has type tau for 4 steps? Yes, because I said up to, right? And that intuition is captured by a lemma called, the type interpretations are downward closed, or it's a monotonicity property. Anytime we have V belongs to V tau for k steps, we have to be able to prove that V belongs to type tau for j steps for any j less than or equal to k. Okay? You can call it types are downward closed or monotonicity. We're going to have to prove this lemma. All right, I should let everyone go for lunch at this point. We'll continue with this tomorrow. All right?